What type of force holds a nucleus together? If we look at a simple nucleus of helium-4, for example, it has two protons and two neutrons combined into a single region of space. Now, the neutrons have no electric charge, but the protons both have a positive electric charge. Since two like charges repel one another, why doesn't the nucleus just fly apart? Well, there's another type of force called the strong force, or the strong nuclear force, which attracts both neutrons and protons together at very short distances. So this type of force only works at very, very short ranges, typically at distances less than 10 to the minus 15 meters. And at distances of this or less, this strong force overwhelms the electromagnetic repulsion from the two neighbouring protons, and this allows the nucleus to hold its stable formation. But some nuclei are more stable than others, and the more stable a nucleus, the lower its probability of decay. So in the last lesson, we defined binding energy to be the energy required to separate all the nucleons in a nucleus. So we would expect larger nuclei to have larger binding energies, simply because there are more nucleons to pull apart. But this doesn't mean larger nuclei are more stable. In order to assess the stability of a particular nucleus, we need to calculate the binding energy per nucleon. And the binding energy per nucleon is simply the total energy needed to completely separate all nucleons in a nucleus, divided by the number of nucleons in that nucleus. So let's say we have two nuclei with the same mass number, so the same number of nucleons in the nucleus, but the nucleus on the left-hand side has a higher binding energy than the nucleus on the right-hand side. So given this information, which nucleus is more stable? Well, the higher the binding energy per nucleon, the more stable the nucleus is. Both nuclei have the same number of nucleons, in other words, the same mass number, but the left nucleus has a higher binding energy per nucleon, so the left nucleus is more stable and less likely to decay. What if we were to plot various nuclei of different sizes with their binding energy per nucleon? What would the graph look like? So we'd end up with this type of graph, where at the bottom here we have the number of nucleons within a nucleus, so that's the sum total of the protons plus neutrons in a nucleus. And on the y-axis, we have the binding energy per nucleon, which is measured in mega electron volts. And from the previous lesson, we showed that an electron volt is simply another unit for energy and is equal to 1.60 times 10 to the minus 19 joules. And 1 mega electron volt is 1,000,000 electron volts. So on the left-hand side, we have lighter nuclei. And at point A, we start with hydrogen, which has a mass number of 1. As we increase the mass number, or the number of nucleons within the nucleus, the binding energy per nucleon increases and hits a maximum at a mass number of 56. And this happens to be an isotope of iron. Now, when we increase the mass number further, then the binding energy per nucleon starts to decrease. And at point C, we would have the heavier elements. So where on this graph would we find a nucleus with the highest stability? Would it be at point A, point B, or point C? Well, at point B, we have the highest binding energy per nucleon, and this is about 8 mega electron volts, and this happens to be the ion 56. Any element heavier than this can undergo nuclear fission, where a large nucleus, when bombarded by neutrons, may break into two smaller nuclei. These two smaller nuclei will have binding energies per nucleon higher than the parent nuclei. In other words, the two smaller nuclei are more stable than its parent nucleus. An example of this induced nuclear fission is when uranium-235 absorbs a neutron and splits into two lighter and more stable nuclei, barium and krypton, with mass numbers 141 and 92. And it also spits out 3 more neutrons, plus some energy. If we look back at our graph, we can see barium and krypton are more stable because the binding energy per nucleon increases when the mass number decreases, until we reach a mass number of 56. Now, between A and B on the graph, these lighter nuclei can combine and fuse to form larger nuclei. This requires very high pressures and temperatures and occur naturally in the center of stars. Like the fission reaction above, fusion releases energy and the resulting nucleus has a higher binding energy per nucleon. An example of a fusion reaction could be this one, where we have two hydrogen nuclei, and when they fuse together, they form a helium nucleus with a mass number of 3, so 2 protons and 1 neutron. And if we look back at our graph, the daughter nucleus, the helium here, has a higher binding energy per nucleon than the hydrogen. So let's do a quick question. The binding energy of a helium-4 nucleus is 28.4 mega electron volts. Calculate the binding energy per nucleon. So we know that a helium-4 nucleus has 2 protons and 2 neutrons, and the total number of nucleons in helium-4 is 4. Now, to work out the binding energy per nucleon, we need to divide the binding energy of the nucleus by the number of nucleons in that nucleus. So we've got 28.4 mega electron volts divided by 4 nucleons. So the binding energy per nucleon for helium-4 is 7.1 mega electron volts.